Hey guys, welcome to the fifth session of number systems in the playlist of quantitative aptitude for CAT and other management entrance tests. As I have been saying since the past few lectures that this is going to be forming your core foundation for quant in several exams and even your college placement exams, as you can see on the screen. With that said, I think so far you all might have gotten comfortable with number tree, primes, composites, and factors. So let's take it up a notch. This time we are talking about factorization, or to be more specific, factorization you have already done for numbers. We are going to be talking about prime factorization because prime factorization is going to be very helpful for several use cases. But first, let's understand what it is. To be very specific, what prime factorization is, right? So as we have done factorization is nothing but finding factors of a number. We have already done it for 6 and 56 as in last sessions. So I just need to do prime factorization. Out of these all factors, I know for sure that 2 and 3 are prime numbers. Similarly for 56, 2 and 7 are prime numbers. Out of all these. So apart from these numbers, none of them are prime. And this is my prime factorization. But it doesn't stop there. I need to represent this number only in their multiple. That means in 6 case that will be 2 into 3, and in 56 case that would be 2 raised to something into 7 raised to something, or I can write it like 2 cube into 7. That is called prime factorization. I am writing it in the multiple, but of course only using prime numbers. So you can always find it like this, like trying several combinations, but what will be the fastest way? That's what we are more interested in, because you will find several cases in exam where you need to find these prime factor forms. And see, one such method is, I think all of you are familiar with it, making such a continuously dividing table. In case of 56, I will divide it by the greatest known prime number that I know will completely divide it. That in my case, I didn't know it was 7. Without doing this section of multiplication, I wouldn't knowing whether it is 7 or not. So I will start with 2. And as I keep dividing, I will find 7. So I can write it like 2 cube into 7. Similarly for 64, let's take a new number. I will keep dividing it until I am left with the prime number at the last. I will be left with 2 raised to 6. So this is how you do prime factorization. And if you continue, this topic is also helpful for identifying squares, even perfect squares, to be more precise. So let's take a prime square first. 49, you can write it like this, 7 into 7. And for a composite square like 12, it will be 144. And I'm sure you guys remember 144 is a perfect square of 12 from the square and cube chart that I shared with you. So I will start dividing by 2 and eventually end up with 3 as the last prime. And I can represent it like this, 2 raised to 4 into 3 square. And I can also simplify it further by taking 2 common. What do you notice here? Well, all these square values will have 2 multiplied in them, every individual prime number. For primes it is quite simple because you will only know squares of prime. It is quite simple because only single number will be there and you will definitely identify that it is a square. But for composite primes, how do you know? In that case, every prime number which you are using to represent the multiplication, all of their power should be even number, or to be more precise, they have to be in the multiples of 2. Here as you can see, they were 4 and 2. It can also be 8, 6, even 12, any power which is a multiple of 2. In that will be square. Similar for cubes, it should be multiple of 3. Common sense, right? But mind well, all of the prime numbers, like for 144 it was 2 and 3, and there might be some number like 2 into 5 into 6. No, that's not. 2 into 5 into 7 into 3, and powers would be different, but all of them should have power in the multiple of 2. That's the scenario and condition. With that said, let's do a easy question just to check your concept depth. So what is the least number by which I should multiply 2124 so that its final product is a perfect square and also perfect cube? Mind well, these are two different questions. That's why I marked A and B. So I need to find two numbers, one which will make it a perfect square by multiplying and one which will make it a perfect cube. So first I will just do this continuous division until I find that okay, 59 is coming and I am unable to divide it further. It's okay if you don't remember whether this is the prime or not, just keep doing until you can find it. And I can write it like this, 2 square 3 square into 59. So obviously from this we can see to make 2124 a perfect square we are lacking another 59. So obviously the first answer would be I need to increase the power of 59 by 1, that is multiply 59 to make it a perfect square. For next part, as I said earlier, for squares we need a power in the multiple of 2. For cubes we need power in the multiple of 3's. So obviously I need to increase the power of 2 and 3 by 1 and the power of 59 by 2 to make it a perfect cube. So in that way our final answer would be 2 into 3 into 59 square, which will end up giving me to 20,886. That is the number I need to multiply by this to make 2124 a perfect square. I'm sure that provided a good understanding of what we are doing, right? Let's solve another set. What is the least number by which this number must be divided so the remainder is 0? And the quotient is a perfect square or a perfect cube. Now you have to quite familiar with quotient, remainder and divisor and dividend to solve this. I'm sure you can find it up on Google. At least that's the bare minimum you should do. And just a quick glance what these terms are. I'm sure many are quite lethargic to even search that, and at least search the meaning of lethargic. Okay, so divisor is the number by which you are dividing and dividend is the number being divided. Quotient is what you get at the above and remainder is what you get left over when you cannot divide it completely. And of course this is not for decimal divisions, this is for perfectly divisible numbers. So let's try with our number. Fortunately it is already given in the power or prime factored form, so we don't need to do much. Just we will simply know that if I am doing this 3 times 8, sorry, 3 raised to 8 into 5 raised to 12 by multiplying or dividing by 15, I'll be left with something like this. What I need to do is make it perfect square, right? So for making a number perfect square, we all know it has to become multiple of 2. For that, I removed 1 power from both. That's why I took 3 and 5 outside and make it other a quotient. Similarly, for making it a perfect cube, already for 3, 9 is a multiple of 3. But what about 5? Again, it has to be 12. So I only need to take care of 5 now. That's why I will divide it by 5. So our answers are 15 and 5. I'm sure this was quite easy. If you know the meaning of these terms, that is the bare minimum requirement for solving these kinds of question. Now, moving on to a bit of self-practice again. Find the least number by which the following numbers must be multiplied. So the products are perfect square and perfect cube, similar to what we have been doing so far, right? Good practice. And this. Again, this time only difference is the first case we were multiplying and for these you have to divide. So their quotients are perfect square and perfect cube. Both of these kind of question you have already done. So I hope you do this as a self practice as your homework. Now moving on to the next question. If P belongs to N, this symbol which you can see is equal like E. It is not pen. It is P belongs to N. And N is a set of all the natural numbers like 1 to infinity, all the natural numbers. And what is the minimum value of P such that when I find this series P into P less than 1 into P less than P subtracted 2 till 1 is completely divisible by P plus 1. This is the theta question which has been asked in I think Snap or ZAT. So let's try this question. Now here, one thing I am sure, what if I write 3 into 2 into 1? How can I represent it? I can write it like 3 factorial. This inverted exclamation mark. Sorry, it is basic exclamation. Inverted I could say. This exclamation mark is used to represent factorials, which means a multiplication of number with the its predecessors till 1. That's what this is. This p into p minus 1 into p minus 2, this is a factorial. It is just written like this to confuse you. Okay. And I need to find for p factorial by this logic, right? Now I will try to put the value of n equal to 1, 2, 3 and 4 for p. So I can find p plus 1. Now at pi you will definitely notice that when dividing by 5 into 4 into 3 into 2 into 1 by 6, you will get 20. So here the smallest number, minimum value of p, you have already found. The only thing you needed to solve this was that to identify this p into p minus 1 into p minus 2 is nothing but factorial. With that, just if you try now to keep on adding the number, you will find it that yes, p plus 1 is satisfying. So it was an easy question rather. You just needed to take the courage to try the first few numbers and you could have solved it. And with that said, I hope you guys do your homework and see you again in the next lecture. Thank you.